Okay, we're wrapping up continuous spin systems. So today and Friday we're going to set up, let's see, we're going to finish a nonlinear sigma model, and we're going to set up the Koslowitz-Salas transition and talk about the Koslowitz-RG equations. I have one more assignment for you guys, which will deal with both the wave function renormalization that we dealt with last class, so I'll have you derive that, and then we'll look at the Koslowitz-RG equations, and then that'll be it for homeworks. So let me remind you what we're doing since it's been a while. We define the nonlinear sigma model. So, a fairly simple starting point, the idea that you have a continuous degree of freedom, if you will, in your spin variables. And you have a Landau functional or a free energy that has some sort of rotational symmetry. So that would be like an O2 version. The order parameter, which usually would be just the magnetization. You know, you fall into one of these two wells, now has a magnitude and a direction. And what we're considering in the nonlinear sigma model is fluctuations in the direction. Which I've called n, which is the unit vector, and the magnitude of that magnetization would be rho, which I'm keeping fixed. So there's several stages of sort of approximations here. One, we're in this regime where the free energy gives you a well-defined, at least magnitude. There's essentially no fluctuations in that magnitude, but we can still be going around, you know, in the valley that's the minimum of this Landau functional, if you will. So then the action looks like you might expect, where we're only considering n. Okay, just spatial fluctuations of n. But n is also subject to a constraint. And because it's a unit vector, that constraint really gives all the nonlinearities in the action for this model. So the partition function, well, it's a functional integral over n, is usually written such that that constraint occurs there. Just a delta function n squared minus 1. Okay, so we looked at some fluctuations, and then we decided to break up the direction of n so that it's primarily along one direction, whatever, maybe like the x-axis, for example. And we predominantly want to consider the idea that n lies along that axis and has, you know, long wavelength fluctuations or low energy fluctuations. So then we divided things up into sigma and pi. So sigma is that preferred direction, and pi is all the other, you know, 1 to, I guess, n minus 1 directions. And those correspond to your Goldstone modes, or Goldstone bosons in the quantum case. This gives a constraint that we write like that. That constraint's important, especially when you're calculating this Z, the wave function renormalization on your assignment 5. That constraint, the fact that we can write sigma in terms of pi variables, allows us to eliminate sigma from, you know, the action here. And then we wrote the partition function is just a functional integral over all the pi variables. And that final action that we've been dealing with is this ugly thing. That's just, sigma. That's pi. And then this constraint, the delta function, we brought into the exponential, and that gave us a log, which we wrote like this. I think. Okay, so that's basically just defining the nonlinear sigma model. It's an action which, the functional integral over gives you a partition function in the Goldstone modes. So then what we did is we performed an RG analysis on this action. And so that involves all these different steps. We break the pi's into fast and slow modes. I think we Fourier transform first. Fourier transform the K space. So then we have pi's, which are functions of K. Then we did the momentum shell. So which means, component-wise, well, it doesn't matter. We have slow and fast modes, right? And we integrate over the fast modes which occur in this shell. That thins out all these degrees of freedom. Then we rescale and renormalize. So rescale. K prime is B or 1 over B? B. And we've integrated over all these fast modes. So what's left after the integration is the slow modes. So then the renormalization step is redefining the problem in terms of a new renormalized field in K space, defined as inverse Z pi slow modes K, and I think I need a prime here too. That's called rescaling and renormalizing. Okay, ever remember all these steps? So once you do that, you get S prime. And hopefully S prime is self-similar, or you have to argue why it's self-similar. And from the couplings in front of all the terms, here, 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 you get the RG recursion relations. So the relationship between this, say, rescaled and renormalized S and the self-similar S prime gives the RG recursion. Okay, so that's where I finished last class. Okay, it seems simple when you lay it out. And then basically there's just some details in, it's just details in this integration that complicate things with all these Feynman diagrams and so on. So the RG recursion relation I'm going to deal with today looks like this. I'll write it like this. So I have a cutoff from the integral. I have the angular piece, 2 pi over d. And I've got this by expanding that integral I called I1 in terms of delta L, which is defined as b equals an exponential delta L. Cutoff, epsilon is d minus 2. Okay, that's important. And what else don't we know? I think that's it. Okay, so last time I just quickly absorbed this cutoff into t, but I changed my mind about it. So forget that forget the definition of T tilde. I don't think we need it. We're just going to drag that cutoff around everywhere. It just will become part of the, equation for the fixed point. Okay, so that came, I didn't write S prime, but look back in your notes. But that equation basically came from, one of the terms in the renormalized action. And we argued, I think there was something like 4 of these terms. We argued that the other ones don't give any important RG equations, which of course is something, in principle, you could check if you had time. I'm going to turn this into a differential equation to define a beta function. Okay, so I'm in 1 over t, so let's move this over. That's like delta 1 over t, and delta L is already defined as an infinitesimal RG step, so I'll turn it into an integral equation. And let me use k, which is just getting rid of that 2 pi. It's quasi-standard notation. Okay, this should define the non-trivial fixed point. Let's just remember if t is 1 over k, I just want to write this in terms of t. So I want a differential equation in t. That should be minus 1 over k squared. So if I move this over, I should be able to write this as that's epsilon. Now I have changed the sign, so it's plus n minus 2 cut off t squared. So it should be t and t squared, right? Okay. And remember the derivative of one of your coupling constants or whatever you might call that is usually called a beta, subscript, say in this case t. So this is a beta equation or beta function. Remember, in the derivatives of the beta function define the matrix. I only have one equation. In this case, you have a system of equations. You calculate the derivatives of the beta function. The eigenvalues of that matrix are then your, what? I forget. Scaling dimensions, something like that. This is very important. Beta function. Has a name, apparently. Kalin-Symanzik. Beta function. I'll talk about where it arises in different physical theories a bit later. Let's just look at the fixed points first. So you see there's two special cases that are already going to happen. Behavior changes at 2 dimensions and n equals 2. Remember, n equals 2 is like the xy model. So let's just forget the case where all those terms are 0, if we can, and find the non-trivial fixed points that occur by setting that equation equal to 0 and then solving it. So you get a trivial fixed point at 0 temperature, and you get a fixed point that's the analogy to the Wilson-Fisher fixed point. So I'm keeping the cutoff, so it's n minus 2. That's epsilon. Epsilon. So the philosophy is we're doing a perturbative expansion in d minus 2, or near 2 dimensions, say, right? So epsilon's measuring the distance from 2 dimensions. And the non-trivial fixed point, just by solving this equation, is that distance epsilon from 0. So next, let's look at the stability. So what we want to do is find out if flows are relevant or irrelevant at these fixed points, and draw the RG flow. I don't know if I need that subscript t, since there's only one. Okay, so we're just taking a derivative. And just remember how this works. It's, like I said, you typically have a matrix M in the more general case. And M is made up of the derivatives of the beta functions with respect to all the parameters. So they'd be partials, whatever, k, at all k star at the fixed points. And this would give the y's. So the eigenvalues of this matrix are the y's. Y, I don't know. yi's. Okay, but there's only one equation here, so just take the derivative, set it equal to 0, or take the derivative at the fixed points, right? So let's look at the first t star equals 0. That's your y, I don't know, t, I guess, at the trivial fixed point number 1. It's minus epsilon. It's 2 minus d. So whether or not the flows are relevant or irrelevant depend on the sign. So it just depends on whether or not d is greater than 2 or less than 2. So if d is greater than 2, what? It's minus, so it's irrelevant. All right, so it means that's stable, that fixed point. And if it's less than 2, it's positive, so it's relevant. So it reverses direction. At d equals 2. Okay, so there's a consequence for stability of phases at that dimension. So for less than 2, let's see, if you're relevant, then that phase is never stable. So the low temperature phase is never stable at finite temperature at the lower critical dimension, right? It's like the Mermin-Wagner theorem. So let's look at the other fixed point. I didn't name it. Okay, where's the derivative? So take 2 from the t. Oh yeah, and I substitute in, so I have it's linear in t now here. So now I substitute in this thing. Oh. Is that going to work? Yeah, okay, so these KDs and the cutoffs cancel. The n minus 2's cancel. Oh yeah, so I have 2 epsilon. Yeah, that makes sense. So I have plus 2 epsilon minus epsilon. So it's just epsilon. Okay, so that we can put that picture together now. And we can draw 2 pictures, one for d less than 2. All right, so for d less than 2, that fixed point, that non-trivial fixed point, right, it doesn't exist. So it goes to, that fixed point goes to 0 temperature as epsilon goes to 0. So as we start for d bigger, we just flow to, that fixed point just moves as a function of epsilon. So we get a picture that looks like this with one fixed point at t equals 0. And here's t equals infinity. And then see, does this make sense? So for less than 2 dimensions here, right, everything's relevant. So we just flow to the high temperature phase. So for D greater than 2, now that fixed point exists a distance epsilon away. We still have fixed point here. Now we have another fixed point. That's T star. Flows to this fixed point are now irrelevant, which means things are relevant here, which means that this has to be greater than 0, which it is, right? So we have flows that look like that. So the low temperature phase is stable. That's what irrelevant means. You perturb your Hamiltonian, you push it somewhere up this line, and it flows back. So the physics of anything here is governed by that fixed point. This fixed point exists. It's non-trivial. It's unstable, which is just like saying you have a critical temperature, and you have to be exactly at that critical temperature to be at the phase transition, right? And if you're anywhere above, you flow to the infinite temperature, say paramagnetic phase, and anywhere below, in Hamiltonian couplings, you flow to 0. And you also see there's an issue here. You seem to need n greater than 2, right? In order for this to work. Right? Makes sense? So for d greater than 2, n greater than 2, you get a non-trivial fixed point. You can calculate the exponents. Although, what you get in first order and epsilon isn't very enlightening, but still it's possible. So yt was what? Epsilon, which means nu, that's 1 over nu, so nu is 1 over epsilon. Alpha, so from your notes, is equal to this. These exponents are independent of n, but they depend on epsilon. You can keep going, although I guess the only non-trivial thing is if you need the other thermodynamic exponents, you need the other y, right? You need y of h. So you need to know how, right, this is just a temperature coupling. You need to know how a field which couples directly to the order parameter scales into the RG. So that's always fun. Let me just give you the answer. Right, so you need so you can add a term to the action, which is like a magnetic field, dot product with, you know, n, say. So we started up there with quadratic in that gradient, but we need something linear. That's the whole point, right? It's not in the action right now, but what a magnetic field does is couple to, you know, the lowest order odd power, say, of the order parameter. So that gives you all your response functions, you know, susceptibilities and so on. Under the RG, These terms are actually easier to figure out. You're trying to get the scaling dimension via that definition. And what you find, okay, I just wrote this down real quick. So you find, you can check this. I think it's 2 here. You have that integral, that d-dimensional integral. We're going to assume that our fixed point isn't changed. So that's a bit of a subtlety. You know, because usually you have to incorporate this parameter into this matrix here, right? And then diagonalize that. But just real quick and dirty, if we assume that that fixed point doesn't change, then we can just look at, you know, the RG scaling of the term, that's that linear term in the action. So you can do that just to get a feel for the other exponents. And take your b's, expand them out. What is a b is e to the delta L. You'll get something like yeah, that's how these equations look. So you have linear terms in delta L, and then you also have quadratic terms. It was the same when we derived this. I erased it. No, this equation here. This is only the linear term in delta L. Remember? So you do the same to this equation. You on the right-hand side, you'll get d delta L You need that form of I1 in terms of delta L, which I've written here. That's in your notes. You need it for your assignment 5 also. I think that's right. So that'll give you, so then you have a t here. Just plug in t star. Like I said, in principle, you have to solve this system of beta functions, the derivative of the beta functions, but just trust me, it doesn't change the fixed point. So plug in t star, and you'll get something like this. So it's interesting, the, say, scaling dimension for the order parameter coupling field does actually depend on the number of spin components n. And you can get all your exponents from this, including things like the anomalous dimension, eta, what is it, d minus 2y, h plus 2, I think. So check this, I got epsilon over n minus 2. So eta, like the anomalous dimension for 1 occurs linear in epsilon. So that's interesting in principle. So this is all I want to say about the sort of non-trivial fixed point in the nonlinear sigma model. I mean, once you have this equation and this equation, then you can just do all the analysis that I've done really quickly here to understand the behavior of this fixed point. So let me just tell you a couple important points that come from that analysis. Well, first off, as we saw over there, the notion of a lower critical dimension and the Mermin-Wagner theorem. Remember I did that really sketchy, free energy argument about the defect boundaries? This is that same argument on a much firmer footing, in an RG sense. So it's really the nonlinear sigma model that tells you this very important physical fact about, lower critical dimensions and which D and N you can expect ordering and which you can not expect ordering at finite temperature. And so this has consequences for, all sorts of real systems, especially, of course, in 3 dimensions. Once you take this class, if you're in the PhD program, the Mermin-Wagner theorem is on every qual that we give. So you have to understand everything about it. And I think this is the easiest context, or the most sort of complete context to understand things about it. So that disappears as, we'll talk more about this, as D approaches 2. So if you still consider n greater than 2, like in this equation, then there are physical magnets, say, that have that symmetry. So for example, the Heisenberg model. So this would tell you that the Heisenberg model which has 3 component spins, S dot S, Ij, in the Hamiltonian. That's n equals 3. Right, so these have finite t transitions for d greater than 2. Okay. Oh, same for, say, the XY model. I'll talk about this one lots. Not as obvious because you're dividing by 0 there, but these marginal cases are always a bit sketchy, but at least for Heisenberg, for d greater than 2, these have finite temperature transitions. So all you need to know is the Hamiltonian. If you have a magnetic system, that has a continuous degree of freedom, all you need to know is under what group symmetry that is invariant under. Right? That's a very fundamental part of modeling condensed matter systems, say. Is it S dot S with n equals 3? Is it XY? Right? XY models always, are always the go-to models for quantum systems that have complex wave functions, and the order occurs in the phase of the wave function, right? Because it's like e to the I theta. So that's just an O2 variable, say. And the combination of this non-trivial fixed point, the nonlinear sigma model, and these O2 systems gives some of the most precise tests for quantum field theory. All this is quantum field theory, right? So these give our experimental test. So this is my favorite one. LIPA, I guess, 2003. They sent a experiment on the space shuttle with helium to measure alpha in microgravity, and it was like specifically to test, you know, that alpha. Calculated from the nonlinear sigma model.
So why did they need it to do it in microgravity?
Yeah, that's a good question. I know why they need cold atoms in microgravity. So there's current, I forget what the name is, but there's current labs. There's a cold atoms lab that you can put experiments in orbit, because when we put atoms in a trap, they sink because of gravity, but I guess gravity also affects these specific heat measure. Experiment. Do you know why? Any experimentalists know why? I don't know why. Maybe it was just a gimmick. Yeah, if you read this paper, it's like on the space shuttle. And they got alpha, let's see.
Are you sure that vortices are not relevant to this question?
I'm going to talk about vortices, but
right.
in this case...
They're going to have a problem with everything rotating.
Yeah, I heard the bigger problem is everything shakes up there. They have a vibration isolation issue. It's like, you know. So that's what they got. It doesn't seem all that precise, but I guess. Okay, so if you plug it, you're not going to get that answer to first order in epsilon. So I think you have to do a fourth order in epsilon to get anywhere close. But so, you know, in principle, you know what to do. All you have to do is become an expert in Feynman diagrams, and you can compete with these calculations, right? But I'll write some theoretical results. Okay, so it's, I guess the point is for helium, oh, I forgot to say helium here. What did I say? It's the phase of the complex wave function. So your phase becomes long-range ordered. Your wave function becomes non-local in that sense. So it's O2, O2. So in principle, it's 3D O2. So your epsilon's 1. Yeah. Mm-hmm. Oh well, at least the sign's right. So, for loops in the continuum. Basically, you know, the sophisticated version of what we're doing here, that gives, I don't have references for these. 0.01126. 0.1, yeah, it's not bad. The last I heard, lattice Monte Carlo. Was worse, which I have trouble believing. And there's a really accurate variational RG, which is also on the lattice. One, two, five. Actually, it's got a big error bar. I just realized, I don't know if there's a bootstrap calculation for this. I don't know if it's possible here or not. Remember I said the bootstraps were the conformal bootstrap was the most accurate numerical value for the Wilson-Fisher fixed point. Okay, so nonlinear sigma model, relevant. Test of quantum field theory gives you experimental access. Again, the whole point of this class is the idea that these exponents are universal, right? So you can do something as crazy as specific heat of helium in the space shuttle and Monte Carlo and get the same answer. And it just has to do with the dimension, right? And the symmetry properties of essentially, say the order parameter and the invariance, the group, under group transformations of the original Hamiltonian. That's all that matters for universality. Okay, so we're going to move to 2 dimensions. Any questions about this?
Okay, so I'm just wondering how you go from alpha is equal to T minus 2 plus epsilon over epsilon to these values?
Yeah, so you have terms that are order epsilon squared, or 3, 4. So I think you're up here somewhere. So you need all those diagrams that are like, things you can't even imagine. It's like people made a career off doing those types of calculations, especially in the past. So those are pretty, I don't know how the number of those diagrams proliferates, but it's a huge amount of counting. There's like software packages that help you with diagrammatics and everything like that. So it was a big industry. Maybe it still is. People here do 2-loop calculations, right, all the time. So yeah, so it makes you wonder, right? Because this is a really simple calculation. This is like the simplest thing you can do numerically. Makes you wonder why you would do epsilon expansions, but I'm just kidding. They're useful conceptually. Other questions? Okay, so this class is all about understanding all these Nobel Prizes, right? Wilson and Fisher got a Nobel Prize. Costas-Salas just got the Nobel Prize this year. There's a Nobel Prize hidden in 2 dimensions from this beta function that David Gross got when I was in Santa Barbara. I think it was 2004. So let's look at the 2D version. So when you have 2 dimensions, where's my beta? I'll rewrite it. So let's just now restrict ourselves to 2 dimensions. Okay, these are all bulk. This is 3D. This is the lambda transition. 2D is special. And your beta function is very simple in a way. Has higher order terms, of course. So we won't talk about it here, but this is a toy model for quark confinement in QCD. So you'll get that essentially same beta equation where the epsilon dependence is eliminated if you study quantum chromodynamics, which is the theory of how quarks are confined in a nucleus.
Hang on, is this a toy model for quark confinement in 2 or 3D?
I think it's 40.
Right.
Don't ask. Don't ask. I think it's 40. So you'll see it in some other context. And people saw it maybe first, or maybe it's most well studied in that other context. And this is what people in the 70s this is the problem people in the 70s were interested in. It wasn't space shuttle experiments, it was the problem of quarks and why they look free at short distances, but then they're confined very tightly, right? So you can't rip them out of the nucleus. I'm going to say 40. You can check that. Pardon?
I think it's true.
I think it's true, right? I think it's 40.
Theory 40.
Yeah, it's Yang Mills, yeah. I'm not going to talk about this. I just want to set the stage for why people, study this beta function. So in principle, we could do this if I knew how. Maybe in 2 years I'll do this. But so in principle, you can calculate that spin-spin correlation function in, the D equals 2 model, right? So from the beta functions or from the constraints. And that correlation function, so it's a set of differential equations because we're calculating from differential equations. So you can use this method of characteristics to introduce a parameter. So you parameterize basically the solution. You can think of it as a time. You're parameterizing the spin-spin correlation function, as a function of distance and time. So it's just some parameter, but that 2-point function, which we've always been calling g, is basically small at short times. And large at long times. So this is not in QCD. This is just in our framework. In QCD, what you do is you interpret, this is high energy and low energies. And high energies are, or did I get that backwards? High energies are, when you probe the nucleus at its smallest length scales. I think that makes sense. So I said the quarks are free in that case. And then at long distances, if you try to pull them apart, they're confined. So this function, which, like I say, maybe I would torture you with if I knew how to do it, is the analogy for, it's the same correlation function that occurs in this 4D quantum chromodynamics. And this gives so quarks inside hadrons are free. But they can't be, so it's basically, so if you probe it at very high energies, that makes sense. But as you try to pull them apart, they become impossible to isolate. I don't know how to say that. Right, so that's 1973. Everything was happening at the same time. Early 70s, Wilson Fisher. Gross and Polyakov and all these people were working on these problems. So the form of this correlation function, and the reason that it's small versus large at different values of this parameter is basically the explanation behind what's called asymptotic freedom. quarks are asymptotically free as the distance between them approaches 0. It's like backwards land. So that's why it was a Nobel Prize. And this is a pretty recent one. So it's Gross, Balzer, and Wilczek. So I think that's cool, and you know, you'll hear about it in a high energy class. But for us, I want to move away from this and into the special case where an n equals 2. And that was basically the, you know, subject of this year's Nobel Prize. So that's d equals 2, n equals 2. So then your beta function, the last remaining term, is 0. Okay? Like, do I have my flows still here? No, I just deleted them. You know, for n greater than 2, for d equals 2, okay, if you just look at the relevancy, so that'll be a relevant, you know, the eigenvalue will be relevant for that case, so just, that's important. I don't think I said this before. So Heisenberg, that's the only physical case. Heisenberg model and anything with higher n. N equals 3 and higher. Right, that remaining fixed point is, everything's relevant, so these are all disordered. So 2 is the only case that we don't know, because what happens is our beta function is 0 on the right-hand side. And if we kept going to higher and higher orders in T, for example, you can show that it's 0 to all orders. dl equals 0 to all orders. So that epsilon expansion is basically useless. And that's unfortunate, because that's a physically relevant case. For example, two-dimensional helium, if you absorb it on a substrate. So helium, if you absorb it on a two-dimensional substrate, that's 2 dimensions, and that's n equals 2, right? So there's definitely experimentally accessible cases in condensed matter where you want to know what's going on. And everything we've done with the nonlinear sigma model is completely useless. And I think before Costas-Salas looked at this theory, there was evidence that there was something going on. High temperature series expansion. You know, people could do like kind of perturbative series expansions numerically, which are more common in the 70s. And they saw susceptibility and maybe specific heat divergences. So there were some, you know, indications that at finite temperature something's going on. But whatever it is, it can't be a regular symmetry breaking transition, because if it was, it would have been captured by the nonlinear sigma model. So the question is whether there's some hidden transition in d equals 2, n equals 2. And as I hope you know, there is. So let's look at first the action, the nonlinear sigma model, what the action just looks like. You know, right back to first, you know, the first thing I wrote on the chalkboard today in this special case. And we'll think about that action as we go forward. So I had 1 over 2t d dx, d squared x. Oh. And then grad n squared, so there's 2 components. A equals 1 and a equals 2. And let me put a parameter in front here, which you'll see in the literature called the stiffness parameter. Even though there's only one term in here, I think I had a rho. Yeah, remember I had rho as the fixed value of the order parameter, and I think I called that 1 over t. Let me just put a parameter back in there, and rho s is stiffness. This relates to, I think, probably something that I asked you to calculate in the computational assignment for the XY model. So it's just 1 for now. It's just a parameter that I'm going to drag around. Okay, so that's just the starting point for our action. We just want to specialize this to the fact that our unit vector just has an x and y component, and we still have a constraint. Now I hate these superscripts, but oh well. We have this constraint. And since we're in 2D, we can just imagine replacing this notation with, you know, a rotor, right? It's just a classical rotor. So that's just your unit vector parameterized by the angle. It's a real variable. It's a function of x. And then this term, which has 2 components, something like sine squared theta, then by chain rule, cos squared theta. Squared. Okay, so that's the piece you can put in. You can write this as an action with respect to that theta variable. So we're going to deal with this action, but we're going to be careful when we take the long wavelength limit. So this is what we'll use on Friday. And Let me just note that, we've basically, we've derived this action a long time ago. I mean, what we did was we looked at the Ising model, then we generalized it to the ON model, right? Now we've said n equals 2. But you can also very simply derive this action as a Hamiltonian that comes from microscopics in the XY model. And those microscopics are going to be important for the Clausius-Zallis transition. So it's important to know that we can relate this directly to a microscopic model. So that model's called the XY model. On G over 2, I don't think so. So nearest neighbor spins, which I'll call S dot S, but they're 2 component spins. And I'll write these spins as again, just the rotor variables, such that this Hamiltonian it's cos squared, no, it's cos theta I sine theta j. Oh, no, it's cos cosine sine. I'm an idiot. And then that just gives you through a trig identity this cosine. Okay, so the theta variable is constrained. Something like that. Okay. So which is the same as the constraint on the nonlinear sigma model. And let's consider, like, how do we go from this to that? It's very simple in this case. If you consider a limit where, the difference between the rotor on 2 sites is very small, then you just expand the cosine, right? And that's the equivalent of the long wavelength limit. So this is a critical, I'm going to say, bad assumption for the physics that we're looking for. Okay, but let's come back to that. So then the Hamiltonian is just a ground state, 2Jn. That's where everything's perfectly aligned. Square lattice, let's say, so 2 bonds per site, and everyone's satisfied. And then that term, it's just a ground state energy. Oh, sorry, got rid of the cosine. So just keep in mind there's 2 bond directions in 2D. And then in the continuum, what we're looking at is the difference being, you know, this is just like the lattice derivative. And so we can replace the sum with an integral and get the action back. Ground state energy, J by 2, d squared x. Okay, so we see, again, the assumption that goes into getting the nonlinear sigma model is somehow this thing here. So that, and that's the assumption that's missing the physics. Okay, so let's leave it at that for today. So what I'm going to do is start looking at, so for Cauchy-Lasallas, you can basically just think in terms of the XY Hamiltonian. Okay? You don't need all this machinery of nonlinear sigma model in principle. So they're equivalent under this assumption in the continuum. But we're going to regulate our theory on a lattice and look at, you know, essentially the vortices that violate that assumption and how those vortices give us a new phase transition, which is called the Cauchy-Lasallas transition. Okay, so I should be able to do that on Friday. So all I want to do is talk about KT transition. We're going to look at the Clausewitz recursion relations, but I'm not going to derive them, I don't think. I have them on your homework 5 to fool around with. And then I want to talk a little bit as a kind of an application of the renormalization group about something a little bit different, and that's entanglement scaling in the continuum. And that'll just be one class. So in principle, we have 3 classes left, and I have enough material for 2, although usually I go long. So I think we're in good shape to finish up next week, okay? Bring me your assignment 4s. I have your assignment 3s to give back to you up here, and I have homework 5 question sheet. That's due on March 31st, which is the last day of class. So I know you guys are, you know, constrained for time now, but I have to get the grades in for this course a week after the computational assignment's due. So make sure you have everything into me, you know, as soon as you can, and nothing later than when that computational assignment is due. All right? All right.